My name is Schaffner. Welcome to this talk. I head the SAP Innovation Center Network, which is a place where we explore emerging technologies which have a 2, 3, 4, 5-year range before they hit mainstream or not. And we think about how these technology can have an SAP context or play a role in the future at SAP products or solve a problem for SAP customers. And today, I would like to talk to you about some innovations in the space of human-computer interaction. This talk is titled Brain-Computer Interface, which is one part of it. I will cover a couple of innovations in the space and hope to shed some light on what's next in terms of human-computer interaction as far as technology is concerned. Here's a typology provided by Professor Dennis Wixon. He is a professor at University of Southern California, and he is best known for co-inventing the Surface table from Microsoft. Not the laptop computer, but the actual table, which some of you might remember. And he came up with this evolution of how UIs have evolved over time. The dates that you see on the slide is not when things have been invented, but when they were adopted, mainly by a vast crowd. So that said, command line interfaces, which are obviously still around today, hit mainstream 1965. Graphical user interfaces were sort of the next big thing, which became widely adopted with the breakthrough of Windows 3 and Windows 3.11. And when we speak about so-called natural user interfaces, we speak about touch interaction, objects, context on a device, a concept which has been adopted mainstream with the introduction of the iPhone 4 in the market, which was around 2010. And now some experts in the HCI space, which can be relied upon, say that the next wave of user interfaces will have even more context, and that is context from the user, how the user feels, how the user behaves, what the user does. And there are some hardware innovations in that space which can make a fundamental difference on how we work in the future. And I want to couple a cover of these. The first thing I'd like to talk about is eye tracking technology. Eye tracking technology has actually been around for a long while, and it's widely in use if you think about how software is being validated, right? But it's today done mainly in a way where you invite users to a laboratory and then you expose them basically to some eye tracking. You monitor how they use your software, the eye movement, and then you gain some insights on the product. But the technology underneath that has now become commodity. So here is a USB device from a company called Tobii. It costs 100 euros or so, and if you attach it to your laptop computer, you basically get eye tracking capabilities out of the box if you add 60 seconds or so of calibration. And the next generation of laptops will have this capability built in already. Also desktop screens, some laptops already have it built in, but there's something coming in that respect. And it can do a couple of things already. We're here with a company which SAP engaged with in its SAP IO Foundry program, which is 42, who first brought this to my radar, actually, by showing me a couple of demos on this. For example, making a Wikipedia page scroll down as you read it. So as you go to the last paragraph of what you read, basically you can already trigger a scrolling without any further interaction. But the general idea is that, according to research that people have done, a typical computer user travels almost 2 kilometers per day with his mouse in terms of actual track that they cover. And every mouse interaction takes 1 second on average to go from where the pointer is to where you want the pointer to be. And with eye tracking devices of this sort, you can get this down to 300 milliseconds per interaction by just gazing at, for example, the icon where you want to end up and slightly touching the mouse, which will then land on that point with a very high precision. Okay, we see multiple ways to adopt this. I want to show today a quick demo of some prototype that we have built in that space. And if we could show Ike's screen, then we will see a map of California. And we work here with Esri. That's a maps provider that adds contextual information to maps such as demographics, population, and in this case also how many university graduates we have per county, right? So the little borders here on the map are counties in California, and we can see that the dark ones are those which basically have a high output of university graduates. Because what we're looking to do is we're looking to find a good location to spin up a new innovation center location. And we, of course, want the best and brightest minds to hire in these locations, so we look at the highest output. So if we look here at the Silicon Valley, this is not the Silicon Valley, right? If you look at the Silicon Valley, you see that, for example, if he gazes at the Santa Clara County, that it generates a lot of university graduates. Our grand vision here is that in the future, if you think how this can be useful, think about a screen sharing session in a Skype call, right? Today you can talk, mute your microphone, share your screen, unshare your screen, activate your camera, deactivate your camera. I think in a not so distant future, you'll also be able to share your eye movement. What are you looking at for the other people in the call to see, to have an easier way to have a conversation of what everyone is talking about. And of course, also like to have a mute button for your eye movement if you want to move on to doing something else while you're in that call, which sometimes happens to me. Okay, we already have an innovation center in Palo Alto, it turns out. Let's see where else in California we might go. And it turns out that in Los Angeles County and Orange County combined, most engineering graduates are being produced on aggregate than in any other region in the US. That's why we should be going there, right? So Ike also has a gesture device. That's another USB device, which is commodity today, which allows him to zoom in with this gesture that he just did. And we see that Newport Beach in Orange County is a great location to start up a new innovation center, which is actually where we're going and what will be starting up in the beginning of 2019, something we're very excited about. All right, so far so good. Thanks, Ike, for this. Let's move back to the presentation. Another technology which has been around for a while is AR/VR, right? Virtual reality, augmented reality. We have looked at this technology 3 years ago and we said, oh, these devices are too heavy for everyday use, they're impractical. But it turns out that in recent years, there's lots of traction in terms of new hardware being produced there, which is much more lightweight than basically the classical HoloLens, which has been around for a while. And interesting things can be done with that, especially in the augmented reality space. So I wanted to show you something which we're currently building, basically a scenario where this young lady will now investigate cost. In this case, she looks at travel cost. So what she does here is she uses some AR glasses, not in this video, but if you think about it. And now she puts all travel expenses on this table. So the bigger a ball is, the bigger the expense record for the particular trip that she's looking at. And now she looks into whether it makes sense for these people that she looks at to generate that much travel cost. So the head of sales in EMEA that she just looked at, it's probably reasonable that he does a lot of travel, but now she will find another big one where she is a bit skeptical and sees that the person is actually a service engineer, and she doesn't immediately understand why this guy would generate so much travel costs. So she creates a snapshot of that and sends an email to someone who can deal with it, investigating why the guy has so many business class flights on his expense record. This is actually something which we're actually very close to having done in the lab. This is a bit of a polished video, but if you look at what you can do with a device such as Magic Leap today, it's already quite close. The devil is in the detail, like how accurately can you track an actual ball if you have many of them in the air with a gesture, which this device has to handle, but basically scanning a room, finding a table, spilling some balls on this table is something which is pretty easy today already. And it can be used in a business context. So we want to do more of this kind of stuff at SAP in the near future. Now I'm coming to the actual technology that was in the title of this talk. And this is about brain-computer interfaces. Now, brain-computer interface sounds super esoteric, but it is actually nothing else than a regular EEG device, as you have in a hospital. And again here, similar to other pieces of hardware, we saw a lot of commoditization happening over the recent years, which has led to a situation where you now have a couple of vendors who will sell EEG devices for the so-called prosumer space, right? You can get anything that looks like a bathing cap, right, with a couple of electrodes on it, to a nice-looking headset that maybe supports fewer EEG channels in parallel, but it's really just an EEG measuring device. A simple example of what you can do with it is extract the frequency of things that a user is looking at. So imagine, for example, that someone is gazing at something which flickers at a 15 hertz rate, as opposed to something that flickers at a 17 hertz rate. Turns out, via an EEG device, you can very accurately measure what the user is looking at. That's not so exciting, because this could also be done with an eye tracking device. So we thought about what else could we do where this technology might be useful. So we worked with a customer of ours, Jägermeister. And Jägermeister has a problem in their quality assurance. So here we see basically Jägermeister bottles as they come out of cleaning. So the person sitting there has the job of looking at this stream of bottles. This is 8 bottles per second, and he has to look at whether all bottles are clean or if there is a crack in the glass or something. And if he finds a bottle that needs to be replaced, he has to fish out the bottle while looking at the stream of bottles that pass by, which is mentally very engaging. So that's why he needs to take a break every 15 minutes, because it's so mentally consuming. Now, Jägermeister has already tried to use machine learning to solve this problem, right? So in the computer vision space, you might imagine, let's just hold a camera onto this and see if bottles are broken or dirty. But it turns out that didn't work very well, because the dark green color of these bottles swallows a lot of light, right? Normally, if you hold a transparent glass bottle into the light, you can easily see if it's dirty or if there's a crack or so, but this dark green swallows a lot of light. And also there's the Jägermeister branding, the logo is sort of in the glass, so the surface is very hard to make sense of for a computer vision algorithm. So they had a very low precision for determining with computer vision whether this is good or bad. So what we did now is we went to our partner at the Fraunhofer Institute and tried to go at this problem with the brain-computer interface type of solution. So what we do here is we train users with such a brain-computer interface device while they wear it to look at whether these bottles are good or bad. This can be done at the screen, doesn't have to happen on location. And once this training has been completed, it can be used to basically judge if we're looking at a bottle that is okay or a bottle that needs to be sorted out. And currently, we're averaging at around of an 80% prediction accuracy, which is much better than the machine learning-based solution. And we hope to get it up even more as we look to, at some point, deploy this together with Jägermeister once we gain more experience with this. Okay, this will lead to a situation where the person at Jägermeister will maybe be at their job for longer than 15 minutes or be less mentally engaged. It would even be conceivable that you do things like automatically get the bottle out, because it turns out the signal that you measure, the so-called Oddball Principle, if some element in a series is not what you expect it to be, you basically get a drop of a couple of microvolts on these EEG channels that you can measure, and then you can take action. And this is very consistently happening around 300 milliseconds after the incident. So you could use this to use compressed air, for example, to automatically get the bottle out of the way without the guy having the need to basically take care of removing the bottle while monitoring the stream of bottles. Another potential application of this is call centers, right? So instead of dispatching incoming calls to people in the call center randomly or in a round-robin fashion, we could actually try to take their mental or cognitive workload into account, which is something which might improve the outcome of the conversations that you have. Because if you have mentally more engaged call center agents, you might end up having better customer interactions. So this is what I wanted to talk to you about in terms of brain-computer interaction. Thanks for attending the session. Happy to take any questions you might have. Actually, I think questions are supposed to be had in the room over there, so please join me over there in this room. Thank you very much.